Yes, analytic functions 2, Cauchy-Riemann equations. This is the continuation of the previous discussion in video analytic functions 1. There we have studied the statement of the following theorem which gives necessary and sufficient conditions for a function to be analytic. The theorem says that if the real and imaginary parts u and v of a function f have continuous first order partial derivatives and they satisfy Cauchy-Riemann differential equations curly u by curly x is equal to curly v by curly y and curly u by curly y is equal to minus curly v by curly x, then f is analytic. We now discuss here some mathematical results around these CR equations. First, suppose that f is analytic in a region omega. Then limit delta z goes to 0, f of z plus delta z minus fz over delta z exists and is equal to f dash z. And this is true for all z in omega. We have fz is equal to u plus iota v, and for delta z is equal to delta x plus iota delta y, we write fz plus delta z is equal to ux plus delta x y plus delta y plus iota v x plus delta x y plus delta y. So f dash z can be written as fz plus delta z minus fz. So subtracting real parts, we have ux plus delta x y plus delta y minus uxy. Then subtracting imaginary parts, we have plus iota vx plus delta x y plus delta y minus vxy, and dividing by delta z, which is delta x plus iota delta y. Now let delta z approaches 0 through real values. That is, first delta y is 0 and then delta x goes to 0. In this case, put here delta y is equal to 0. We have f dash z is equal to limit delta x goes to 0 ux plus delta x y minus uxy over delta x plus iota vx plus delta x y minus vxy over delta x. Now since the limit in 1 exists, therefore both the limits in real part and imaginary part exist. And what are they? They are the partial derivatives of u and v with respect to x. So f dash z can be written as f dash z is equal to curly u by curly x plus iota curly v by curly x. We have used this relation to evaluate derivatives of exponential z and log z in the previous video. Now, likewise, if delta z approaches 0 through imaginary values, that is, first delta x is 0 and then delta y goes to 0. In this case, we have f dash z is equal to curly v by curly y minus iota curly u by curly y. Now, equating real and imaginary parts in 3 and 4, we get these CR equations. So if f is analytic, then CR equations are satisfied. Note that CR equations are necessary conditions for the existence of the derivative, but these are not sufficient. The first order partial derivatives of u and v must also be continuous to ensure differentiability. Let uxy is equal to x cube minus y cube over x square plus y square. This is the real part of one of the examples given in books to show that CR equations are satisfied at a point, yet derivative does not exist there. The reason is that partial derivatives are not continuous there. If uxy is this x cube minus y cube over x square plus y square, then limit xy approaches 0, 0, uxy is equal to 0. So this function can be made continuous at origin if we define u0, 0 is equal to 0. But partial derivative is x cube plus 3xy square plus 2y cube over x square plus y square whole square. Now, if xy approaches 0 along this line, y is equal to mx, then curly u by curly x is 1 plus 3m square plus 2mq or 1 plus m square whole square. And this is not independent of m. So limit xy approaches 0, 0, curly u by curly x is not unique, hence does not exist. This means that partial derivative are not continuous at the origin. We consider following example. This show that fz is equal to x cube 1 plus iota minus y cube 1 minus iota over x square plus y square when z not equal to 0. And when z is 0, its value is 0. This function is continuous at origin. And CR equations are also satisfied at origin. But f dash does not exist at origin. The students in the beginning find this example confusing, as it appears that it contradicts the above theorem. But as we have seen, this is not the case, as according to theorem, the partial derivative must be continuous at that point to ensure differentiability. Now, to prove continuity, we can write this fz in polar form. Then this limit z goes to 0, fz is equal to limit r goes to 0, r, and this expression in bracket. Now this expression in bracket is bounded. So when r goes to 0, this approaches 0. So this function is continuous at origin. Now we can write fz as u plus iota v, where u is real part, v is imaginary part, and u equal x cube minus y cube over x square plus y square, and v equals x cube plus y cube over x square plus y square. Also, u at origin is 0 and v at origin is also 0. Why? Because fz is 0 at origin. Now calculate this partial derivative of u with respect to x. By definition, this equal limit x goes to 0, u x0 minus u00 over x. From here, u x0 is put y is equal to 0. This comes out to be x. And u00 is 0. So this equal limit x goes to 0, x over x is equal to 1. Similarly, we can calculate other partial derivatives using definition. So from here we see that curly u by curly x is equal to curly v by curly y. And curly u by curly y is minus curly v by curly x. So CR equations are satisfied at origin. Now we check derivative. Derivative at origin is equal to limit z goes to 0 fz minus f0 over z. And f0 is 0, therefore this equal limit z goes to 0 fz over z. Now substitute here value of fz. Now if x approaches 0 along the path y is equal to mx, then f dash 0 comes out to be equal to this expression. This again is not independent of m. For example, for m is equal to 0, f dash 0 is 1 plus iota by 2. And for m is equal to 2, f dash 2 is equal to 11 plus 23 iota by 25. So f dash 0 does not exist. It may also be noted here that one can view the above example in the context of following theorem, known as Luhmann-Manchow theorem. Luhmann published it in 1923 and Manchow in 1936. F is continuous in a region omega. And if partial derivatives satisfies CR equation throughout the region, then F is analytic in omega. Note that it is not a point-wise statement. As above example shows that CR equations are satisfied at a point, but function is not differentiable at that point. We have this real part in above example, uxy xq minus yq over x square plus y square, vxy xq plus yq over x square plus y square. We can now calculate their partial derivatives. Now, if partial derivatives satisfy CR equation, then we have y is equal to 1 plus minus root 2 x and y is equal to minus 1 plus minus root 2 x. From first relation, that is curly u by curly x is equal to curly v by curly y, we have y is equal to 1 plus minus root 2 x. And from second curly u by curly y is equal to minus curly v by curly x, y is equal to minus 1 plus minus root 2 x. And this is possible only at origin, that is x is 0 and y is also 0. Since partial derivatives do not satisfy CR equation throughout any neighborhood of origin, so Luhmann-Manchow theorem is not applicable. Now, one property of real and imaginary parts of analytic function, the real and imaginary part of analytic functions are also connected with Laplace equation. Then real and imaginary parts are harmonic functions. But note that every harmonic function does not arise in this way. Now suppose f is analytic in a region omega. Then we have these CR equations. Also, we shall study that derivative of analytic function is itself analytic. So the partial derivatives of u and v of all orders are continuous. Also, then mixed derivatives are equal. That is curly square u by curly x square is equal to curly square u by curly x curly y, and curly square v by curly x is equal to curly square v by curly x curly y. From these we get from 5. Differentiating this with respect to x, curly square u by curly x square is equal to curly square v by curly x curly y. And from this second CR equation, curly square u by curly y square is equal to minus curly square v by curly y curly x. Now on using CR equation, curly square u by curly x square plus curly square v by curly y square is equal to curly square v by curly x curly y minus curly square v by curly y curly x. Since mixed derivatives are equal, this curly square v by curly y curly x is equal to curly square v by curly x curly y, and this cancels out and this equal 0. Likewise, we can prove that the imaginary part v also satisfies Laplace equation. Now, a real valued function uxy of real variable x and y defined in a region omega is said to be harmonic if first and second partial derivatives are continuous and satisfy Laplace equation. So, the real and imaginary parts of analytic functions are harmonic functions. If two harmonic functions satisfy CR equation, then V is said to be conjugate harmonic of U. And in the same sense, U is conjugate harmonic of minus V. In physics literature, and in particular in electrostatic, a harmonic function is known as potential function. And this Laplace equation is the potential equation. Now, one more property of the real and imaginary parts of analytic function, we have this function fz is equal to uxy plus iota vxy. Now, this equation uxy is equal to k1, vxy is equal to k2. These are called the level curves, and they form an orthogonal system. That is, each curve in one family is orthogonal to each curve in the other family. This means that at the point of intersection, the tangent line to the curve u is equal to k1 and the tangent line to the curve v is equal to k2 are perpendicular. where we have assumed that derivative is non-zero. To show this, we have to show that the product of the slope of these two tangents is equal to -1. We have this equation uxy is equal to k1. Differentiating both sides, we have curly u by curly x dx plus curly u by curly y dy is equal to 0. From this, we have dy by dx is equal to minus curly u by curly x over curly u by curly y. This u subscript denote that this dy by dx is for u. Similarly, dy by dx for v is equal to minus curly v by curly x over curly v by curly y. On multiplying these two, we have dy by dx of u and dy by dx of v. This equal this expression. Now using CR equations here. On multiplication, we get -1. So the curves u is equal to k1 and v is equal to k2 are orthogonal. Also, if fz is analytic, then the modulus of f dash z can be expressed in terms of Jacobian of u and v with respect to x and y. If fz is analytic, then f dash z is curly u by curly x plus iota curly v by curly x. So mod f dash z square is curly u by curly x square plus curly v by curly x square from here. Now write it as curly u by curly x and second curly u by curly x equal curly v by curly y. And this as curly v by curly x and second curly v by curly x as minus curly u by curly y. And this equal this determinant. Curly u by curly x, curly u by curly y, curly v by curly x, curly v by curly y. So mod f dash z square is the Jacobian of u and v with respect to x and y. It may also be noted here the following formal argument. Let w is equal to f x y, where x and y are real variable. Let z is this complex x plus iota y and z conjugate is x minus iota y. So x is half z plus z conjugate, y is minus 1 by 2 iota z minus z conjugate. We have curly x by curly z half and also curly x by curly z bar half. Curly y by curly z minus half iota and curly y by curly z conjugate half iota. So if the rules of calculus are applicable, we have curly f by curly z is equal to curly f by curly x by curly z plus curly f by curly y by curly z. Now substitute values from above. What we have, curly f by curly z is equal to half curly f by curly x minus iota curly f by curly y. And similarly, curly f by curly z bar is equal to half curly f by curly x plus iota curly f by curly y. Now use CR equations in polar form. In polar form, CR equations are curly f by curly x is equal to minus iota curly f by curly y. In this case, we have curly f by curly z is equal curly f by curly x and curly f by curly z bar is 0. So in this way, it is said that an analytic function is independent of z conjugate and is a function of z alone. These formal arguments supports the point of view that the analytic functions are the true functions of a complex variable and other functions are just functions of two real variables. Now these are references. You can read these two interesting articles on the definition of an analytic function, American Mathematical Monthly. And second, when is a function that satisfies the Cauchy-Riemann equation analytic. Thank you.